In the last video, we saw potentials of spherical distribution of mass. Less trivial non-spherical distributions usually lead to messy algebra, and the potentials usually end up being described by special functions. Yet, ellipsoidal mass distributions are important in astrophysics, since the vertical direction in galaxies is in hydrostatic equilibrium, whereas the radial direction is centrifugally supported. That the radial and vertical direction are supported differently leads to non-axis symmetry and ellipsoidal shapes, like in the galactic bulge. Not only that, disks can also be seen as extremely flattened ellipsoids, so the potential derived for ellipsoidals is applicable to them as well. An ellipsoidal has shape given by this expression, with the semi-axis A and B being similar, whereas C is smaller. To compute their potential, we will do the same procedure as we did for spherical symmetric distributions. What we did was that we considered a spherically symmetrical shell, and then we integrated over the shells. We're going to do the same thing. Now, the difference is that the shells, in this case, are going to be thin ellipsoids. These thin ellipsoidal shells are called homoeoids. An homoeoid is a thin shell that is bounded by two similar surfaces with nearly identical shape and orientation. What is shown here is a cross-section of an homoeoid, like the two-dimensional section of a three-dimensional spherical shell. But in this case, it's a section of a three-dimensional ellipsoidal shell. If we consider the ellipsoidal shape, then we write here the expression for the surface of the ellipsoid, where beta is constant. The homoeoid will be bound by two surfaces of same semi-axis A, B, and C, but having different values of beta. The quantity beta labels the homoeoid. You'll also notice that a spherical shell is a symmetric case of an homoeoid, where A is equal to B and equal to C, and beta is equal to 1. So we're interested in the mass. Let's say that this homoeoid has homogeneous density. To find the mass of the homoeoid, then we need to know the volume. That is a geometrical problem. So the volume of an ellipsoid of semi-axis A beta, B beta, and C beta is then given by this expression, 4 pi over 3 ABC times B cubed. Now let's simplify that we have an ellipsoid where A is equal to B, which is usually the case in astrophysics, and C is the flattened direction, flattened by the eccentricity, so times the square root of 1 minus the eccentricity squared. Substitute that in the volume. That's the volume then that we have. We got rid of B and C and write that in terms of E. Now, we take the derivative of this volume with respect to beta, and that gives us the volume of an homoeoid. That is the infinitesimal volume that is within two concentric ellipsoids. So if you consider that in this thin shell, the density is constant, we can calculate the mass d big M of the homoeoid. We simply multiply this by rho. Now, let's switch to a variable here. Let's call this variable m, not confuse that with mass. M is equal to, that's the long axis. So I have this expression then for the mass of the homoeoid. Notice that for a spherical system, this indeed reduces to the usual formula. For a spherical system, E is equal to 0 and M is equal to R. Let's compute now the potential of the homoeoid.